Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think yesterday we were discussing about the nomenclature of heterocyclic compounds and what are the certain rule. What are the suffixes are used, how to give actual name of that heterocyclic compound according to common name as well as systematic name that we have discussed in detail. Today what we are going to discuss, we are going to discuss about the 5-membered heterocyclic compound over here. First one is a 5-membered heterocyclic 5-membered heterocyclic compounds, and as we know that first compound is a furan that we are going to study over here. First compound, which is a furan, and as we know that furan has a structure that also we know that, but how to synthesize that furan in the laboratory, that we are going to see. First one, synthesis of furan. Let us see, here is a synthesis of furan that we are going to study here. Synthesis of furan, and this synthesis of furan can be carried out by using well-known reaction which is known as Polynuclear synthesis. This is known as a Polynuclear synthesis, which is also known as a Polynuclear synthesis. Polynuclear is a scientist. He discovered the method for the synthesis of 5-membered heterocyclic aromatic compound. As we know that furan is a 5-membered heterocyclic compound. First we are discussing about the synthesis of furan or the preparation of the furan. First one, from 1,4-diketone. First, that furan will be prepared from 1,4-diketone, which is also known as acetone. Acetone, which is a starting material. He had used for the synthesis of furan. What he did, acetone on heating with P2O5 phosphorus pentoxide undergoes cyclization and forms 2,4-dimethyl furan. This is a very simple method for the preparation of furan or the synthesis of furan. Acetonyl acetone. First one, acetonyl acetone. First what he did, acetone on heating, acetone on heating with P2O5 phosphorus pentoxide, with P2O5 undergoes P2O5 undergoes under undergoes cyclization and forms 2,5-dimethyl furan. 2,5-dimethyl furan. This is a very simplest one sentence procedure for the preparation of furan or the synthesis of furan. Let us see here. Acetonyl acetone on heating with P2O5 undergoes cyclization and forms 2,5-dimethyl furan. First of all, you know the structure of, here I am showing the structure. You can see here, this is the structure which I have drawn here. Here remember, this is nothing but as a methyl group. I am showing over here CH3. If you start from here 1, 2, 3, 4, 5, 6, but common name is acetonyl acetone or 2,5-diketohexane, you can remember, and this is the compound 2,5-hexane dione. We can call it, this is the common name of this compound is a acetone, or the IUPAC name of this compound is 2,5. At 2 and 5 position, ketone is present, 2,5-hexane dione. Di means 2, ONE means ketone groups are present, and therefore the IUPAC name is given to this compound is a 2,5-hexane dione, or the common name of this compound is acetonyl acetone. And now when this compound treated with P2O5, which is used as an catalyst, undergoes a cyclization, acetonyl acetone on heating. So here after the heating, cyclization takes place, and the temperature is kept around 140 to 150 degrees centigrade. That is the temperature kept during this process, and after the cyclization, the resulting compound obtained will be this one. You can see clearly here methyl group and another methyl group which is present over here. You can write methyl groups in this way, or for suitably you can show this properly. This is the structure of furan, where one methyl group I am showing over here, another methyl group which I am showing over here, and as we know that the heteroatom should get the number 1. So 1, 2, 3, 4, 5. So at 2 and 5 position, this is the aromatic moiety, furan moiety. It will be easily prepared in the laboratory by using as the well-known reaction is a Polynuclear synthesis. Polynuclear is a scientist name. He synthesized this type of the 5-membered aromatic heterocyclic compound, and therefore the name is given, the common name of this compound is a furan, but the IUPAC name of this compound 2,4-dimethyl let us see, at 2 position methyl group as well as 5 position methyl group. 2 methyl groups are there, therefore we can call it as a dimethyl. So 2,5 dimethyl furan, and the side product, so water molecule is evolved during this process, and this is a very good method for the synthesis of furan. Now reactions of furan. Just now we have seen synthesis of furan, or you can call it as a polynuclear synthesis of furan. Describe the synthesis of furan, or discuss the synthesis of, or discuss the polynuclear synthesis of furan. Depending upon the nature of the question, you can answer it. The answer should be specific. In one sentence, everything is involved here. Aceto, nil acetone on heating with P2O5 phosphorus pentoxide undergoes cyclization and forms 2,5-dimethyl furan. Whatever the sentence written over here, which is systematically represented on blackboard, the reaction, or this is a figure which tells more about this. See the representation of that reaction, or this is a presentation of the reaction. Aceto, nil acetone, or this is the IUPAC name of this compound is 2,5-hexane diol P2O5, used as an catalyst. On heating, cyclization takes place, and the temperature is kept of that reaction is 140 to 150 degrees centigrade, and the resulting compound obtained is known as 2,5-dimethyl furan. So this is a synthetic part we have learned, and now moving toward the properties of furan, or we can say reactions of furan. Remember here reactions of furan. So here just remember reactions of furan. That is a reaction of furan. Reaction of furan. And at what position? If you remember the structure of furan, as we know that the structure of furan is this one. This is the structure of furan, and the common name of this furan, the numbering system, the heteroatom should get the first number. So according to it, heteroatom I am denoting by number 1, 2, 3, 4 and 5. Now the common name of this compound, as we know that it is a furan, as well as IUPAC name or the systematic name, as we know that oxygen atom, so we can call it as a oxa plus. It is a 5-membered ring, unsaturated compound, so the suffix should be used is OLE, and therefore oxa A you can remove from it, or what we can call it as a discard from this, and the resulting compound whatever obtained you can call it as a oxole, which is a systematic name of this furan. Now the reaction, whether if you see here these 2 and 5 position are chemically equivalent, identical you can say, or it is a chemically equivalent position 2 and 5. Similarly, if you see here the symmetrical molecule, here 3 and 4 position one and the same, and therefore, and as we know that the tendency of the aromatic compound, what is that? What are the natural tendency or the important characteristic of aromatic compound? They readily undergoes electrophilic substitution reaction. But here we know the aromatic compound is a benzene, simple aromatic compound benzene. When it undergoes electrophilic substitution reaction, there are 6 hydrogen atom, all the hydrogen atoms are identical. When it undergoes as electrophilic substitution reaction, out of 6 electron, all are the identical, so resulting compound we are getting, that is a monosubstituted benzene. Once that monosubstituted benzene is formed, that monosubstituted benzene, whatever the remaining 5 proton, on all those 5 proton are not chemically equivalent, they are not identical, because monosubstituted benzene has divided, or it has a symmetry, and therefore there are 3 distinct protons are absorbed in monosubstituted benzene with respect to the substituent. 2 are designated as ortho position with respect to the substituent. 2 position are designated as meta, and exactly opposite, that is a para. So these kind of the 3 positions are identified in a monosubstituted benzene, and when the electrophilic substitution carried out on monosubstituted benzene, there is problem, or that substituent is called as a director, whether they are ortho para director or meta director, depending upon the nature of that substituent. If the substituent is electron releasing group or electron donating group, then the electrophilic substitution reaction exclusively gives at ortho and para position. When in an organic compound more than one products are formed, there is always competition between products. One generally form in major and another should be minor. And other electronic factor which modifies the reactivity of the organic compound, and depending upon that we are getting that. But here why I am discussing that benzene as a case over here you can see whether the electrophilic substitution takes place at 2 or 5 position or 3 or 4 position. That is the main question. In general, you should remember the electrophilic substitution reaction which occur at 2 2 position here. Just remember why the electrophilic substitution occur at 2 position. The answer of that question we would discuss shortly, but here you remember one sentence: furan undergoes electrophilic substitution reaction at 2 position. Furan undergoes electrophilic substitution reaction at 2 position. You can underline here at 2 position. Why it undergoes as a 2 position? Let's see here the reason behind it. Let us see. Those are knowing the concept of the answer would be present. Those are knowing resonating structure better way. Then you will get the answer why furan undergoes electrophilic substitution reaction at 2 position. Let's see here. Let us assume E stand for as electrophile, and that 5-membered ring, it can act as a nucleophile. And as we know that general trend to occur organic reaction, one of the species, either reactant or the substrate, if it is in nucleophilic in nature, your reagent must be electrophilic in nature, because for reaction to occur there must be movement of electron. When movement of electron takes place, there is a formation of the bond occurs, and when that new carbon-carbon bond forms, there will be a possibility of reactions. So here remember, when this electrophile, let us consider here, if it is attack at, let's see here, at 2 position, positive charge comes at 3 position, right? Now electrophilic substitution reaction, when, let us see, this is a structure number first, and when the, let's see here, if electrophile is attack at 3 position, let us assume that positive charge at this position, and now this is a transition state, or what we can call it as a sigma complex. Now this double bond shifted from here to here, what do you get? You are going to get structure here O, then E, and hydrogen atom you can write as it is, positive charge come on it. Now see the lone pair which is present here. So let us, I think, let us draw properly over here so that we can draw the resonating structure. I am trying to explain why furan undergoes electrophilic substitution reaction at 2 position, that I am trying to explain over here. So this is a Furan electrophile. Suppose let us see here, when it is attacking over there, you are going to get oxygen atom here. Here is the electrophile, hydrogen atom, positive charge over here, and this double bond is here. And now resonating structure, when this double bond shifted from here to here, we can show the resonating structure over here. Double bond here, positive charge comes on at this corner point, electrophile and EH here. Now the lone pair which is present here we can neutralize, so that we will get another structure like this. O, positive charge comes on that oxygen atom, here E, here H. Now there is a loss of, suppose proton is there, that goes there, this form over there, and lone pair comes on this side. You will get this type of the compound here is electrophile, we can show here at 2 position. Suppose let us consider, let us assume that in an furan, if electrophile is attacked this manner, what would happen? After that, oxygen atom here we can show electrophile EH, positive charge on it. Now after that we can show the resonating structure over here. Here this can neutralize this bond, oxygen atom, here positive charge, double bond here is the electrophile EH. Then after that, loss of proton, this way form as a double, so we cannot show. So neutralizing this, so you will get number of structures. Suppose here is a electrophile, lone pair comes on its 1 and 2 structure, but in this case 1, 2, 3 and 4 structures. When the resonating structure goes on increasing, the stability of that compound goes on increasing, and therefore why furan undergoes electrophilic substitution reaction at 2 position, that could be the answer, because there are the number of resonating structures are present over there, and therefore preferentially that shows as 2 position. Or in other way around, in one shot we can show as a electrophilic substitution reaction. Let's see here, right? And then electrophile over. General we are talking about when lone pair present on it, this lone pair forming double bond here, and this double bond shifted from here to here, and this double bond attacking on it, so that we are going to get the product, this one O. Here is a double bond, one double bond here, and the electrophile attack over there. There is a hydrogen atom. Now is a positive charge comes on it, and after that there is a loss of proton, form double bond. This double bond shifted from here to here, and negative that positive charge get neutralized, and we are going to get aromatization is back, and electrophile preferentially attack at 2 position. This one electrophilic attack at 2 position, and therefore it is a one way of showing that. If you trying to show that at 3 position, suppose here is a electrophile. Let's say here electrophile, when lone pair, double bond there, and this double bond is not going to attack over there because this is shifting here to here, and if you show here again there is a unstable transition state is formed over there like this. Suppose here O and electrophile H, positive charge over there, and once again this type of the impossible transition states are formed. Prepare, this is a readily occurring transition state, and therefore always remember furan undergoes electrophilic substitution reaction at 2 position, and that's the case. And some of the reaction which is shown by furan why at 2 position, the synthesis of furan we have seen, and in our upcoming lectures we will discuss about the remaining reaction of that furan in our upcoming lectures. Till then, have a nice day. Thank you.